Yeah, so I'm going to talk about autocorrelation and meter finding. Let's harness a couple of intuitions first. My larger research question is how harmony contributes to our feeling of strong beats. How harmony informs the way that we hear meter, and how it doesn't inform the way that we hear meter. So if you hear "O Canada," you probably hear that in 4, or it's either quadruple or it's duple. If you hear it played, and even if the performer doesn't make anything louder than anything else, you still probably hear this in duple or quadruple. Why? Well, one reason is that you've got this series of changing numbers of note attacks. So right at the beginning of the example, you've got 4 note attacks, and then you've got 1 note attack, and then 3 note attacks, and then 1 note attack, and that's going to encourage you to hear certain things as more accented than others, and the accents appear in a duple or quadruple pattern. But also, you can look at the triads that are being used and say, golly gosh, there's a alternation between F and C triads that's going to also encourage a duple or quadruple grouping here. But of course these are interconnected. Note attacks occur because harmonies change, and harmonies change when note attacks occur. So these are intertwined. And so I want to try to tease apart harmony's role through a little computational corpus analysis. What I'm going to do is model a loudness-based or note attack-based meter finding, and then I'm going to model a harmony-based meter finding. I'll compare and contrast the results of those two, and then discuss what they show us. So the algorithm I'm using is autocorrelation, which is a very simple example of machine learning. It's a very simple approach. And let's pretend that I cite a bunch of people here. This is used up and down. If you were listening to a song that went like boom, chick, boom, chick, boom, chick, boom, chick, well, you'd notice that the same sorts of things tend to occur every 4 events, that the big booms happen every 4 events, and the little booms happen every 4 events, and the chicks happen every 4 events. And we can take this and align it up so that the big booms align with the big booms and the small booms align with the small booms. But the other thing that we might notice is that sort of similar things happen every 2 events. That the small booms align with the big booms and the chicks align with the chicks. If you take the second group of 4 and rotate it by 2, so that what was happening in the 3rd and 4th position now occurs in the 1st and 2nd position. And this is the intuition behind autocorrelation. But I was talking about a sound signal, and what I'm going to be talking about is symbolic representations, symbolic musical representations. And so when we talk about symbolic musical representations, we often approximate peaks in loudness by looking at the number of note attacks that's occurring. And this approach has been shown to be pretty successful across a variety of repertoires. Again, there's a bunch of people who use this. So what I'm going to do is divide a piece into its quickest pulse. Then I'm going to make a vector of the number of note onsets or the number of note attacks that occur at each of those pulses, and I'm going to find recurrent patterns in that vector. So looking at O Canada, again, the fastest pulse is the 8th note there. And so if we just made a vector out of the first measure, you would get 4, because the first event has 4 note onsets, and then there's nothing that happens at the second 8th note, that's 0. Then there's one thing that happens at the third 8th note, that's 1, and so on. And so that's how we represent the number of note attacks. Then what we do is we take this onset vector, this note attack vector, and compare it to vectors created by rotating that prime vector. So there's the prime version of measures 1 and 2, and just so that we can keep track of what's going on, the beginning of measure 1 is red, the second eighth note is going to be green, and the beginning of measure 2 is yellow. Now, if we rotate it 1, what was last is going to be, what was second is going to become first, and what was first is going to become last, and notice that the yellow 4 has moved over 1. Now, if we compared these two vectors, they wouldn't be very similar at all. The big numbers are aligning with zeros, the zeros are aligning with numbers. These vectors aren't going to look the same. If we rotate it once more, now our green 0 is at the end here, and we have a better lineup with the prime vector because at least numbers, positive numbers are aligning with positive numbers and zeros are aligning with zeros, but it's still not a great correlation. If we rotate it 8 times, we get a pretty good correlation because now big numbers are aligning with big numbers. So what this does now with 8 rotations is measure 2 is beginning the vector. And so we're seeing that the stuff that begins measure 2 looks a lot like the stuff that begins measure 1. And the first eighth note of measure 2 looks a lot like the first eighth note of measure 1, and so on. And so what we can do is correlate these vectors, these rotations of these vectors. So I'm going to show you the correlation coefficients of each of these rotated vectors. They're going to go along by eighth notes on the x-axis there. And so obviously if you correlate a vector to its non-rotated version, you'll get 1. You rotate it once, and it's going to be bad, because that was that first one where the zeros were aligning with positive numbers and the positive numbers were aligning with zeros. You rotate it one more time, and it's okay, because at least positive numbers are aligning with positive numbers. But what starts to get good is when you rotated a half note. This is saying that things that occur a half note into the future look a lot like what's going on right now. Things that begin the next measure look a lot like what's going on right now. And things that occur 2 and 3 measures into the future start looking a lot like what's going on right now. Now we can use this to identify the meter by finding patterns in the peaks with similar magnitudes. So, for instance, the magnitudes at the half note here and the quarter note look the same. So it would say, oh, look at that. There are peaks at every 2 quarter notes. And look at that, there's similar peaks at every quarter note. And so what the algorithm would then say is that the same sorts of things occur at the half and the quarter, and maybe the whole note, maybe the breadth. And so this piece isn't duple or quadruple, and maybe there's a duple type of meter. So this is how the autocorrelation meter finding process works. What's nice about this, it's theory neutral. It's basically an unsupervised approach to meter finding. So for instance, what we're not saying is that we're definitely looking for the loudest events. We're just looking for events that look the same. I don't have a definition of accent that I bring to the table. I'm just looking for things that look the same. And we aren't necessarily even looking for patterns of 2 and 3. I'm not saying that meter is nested groups of duple and triple. I'm just looking for series that look the same. And so what do I apply this to? I use a Music 21 corpus of XML files. I use composers in that corpus that have at least 9 XML files associated with them. That turns out to be Monteverdi, Haydn, Bach, and Beethoven. And I use just the first 4 measures. And what's my ground truth? Yeah. What's my ground truth? It's the file's time signature metadata. And yes, this isn't actually meter. Time signatures do a lot of things, but what they don't say is what the grand meter of a piece is. But the time signature does give us some idea of how the notated music should measurably define. It tells us something. So what do I test? I use F-scores, F1 scores specifically. F1 is the harmonic mean of precision, and recall precision is the correct answers given, the answers that align with the expectations that we would get from that time signature, divided by all the answers that are returned. And recall, which is the correct answers given divided by the correct answers expected. I don't consider information above the notated measure because the time signature information doesn't address that. So if the autocorrelation says that there's a 2-measure hypermeter or something like that, I just don't pay attention to that. I don't bring that into my F-scores because there's no way that I can compare that to a ground truth. I test vectors where each dimension represents the events of the quickest pulse of the piece, as I've already noted, and they're made from representations of note attacks, as I've already talked about, and representations of harmony change, which I haven't talked about yet. Let's go through each. There's 13. So note attacks, this is what I've been talking about so far. You just count the number of notes that start at each time point. And so here we have 4, 0, 1, 0, 3, 0, 3, 0 for this series that we're, or this measure that we're looking at here. But I also do a binary version of this, which just notes whether there are note attacks. And so this will let me test whether magnitude actually matters, whether it matters how many note attacks there are, or just whether there's note attacks. And then finally, I use a no zeros approach, which shows note attacks as sustained through the timeline. So if nothing happens here, I don't say that, I don't put a 0 in the vector, I say that it's a continuation of this event that had 4 note attacks. Why would I do such a thing? It allows us to ask whether simply the relative magnitude of peaks are sufficient for meter funding. So in other words, it means that the method can't correlate silences and inactivity to other silences. It can only use the relative changes in note attacks. It can't rely on the zeros in the vector. It has to only rely on the changes between different amounts of note attacks. So now let's talk about how I represent harmony. The first way that I do it is pitch class change. So in this example here, you've got your F major chord and it moves to a B flat passing tone here, and so the pitch classes that change, you've got a set with F A C, and it moves to a set with F C B flat, so the change is A to B flat. And so that's what I'm tracking here. And so on the PC change thing, you've got 4 because nothing happened before, and you have 4 pitch classes. But here, because there's only 1 pitch class change, you get a 1 in the vector, and so on. So you get 3 here when you move to the G7 or the G dominant chord because there's 3 new pitch classes that are introduced. And then I create a binary and a no zeros vector with that as well. I also represent harmony by using optic set classes. So it's their set classes equivalent up to inversion. So your major triads are going to be O47s, your minor triads would be O37s. So major and minor triads are inequivalent. So this would be an O27, you get a major triad again, and so on. But how am I going to do that? But we should remember, so in order for me to talk about this, we need to remember that computational work in music cognition has shown us that things that occur more frequently in a corpus tend to be heard as more stable and consonant by listeners familiar with that corpus. Again, plenty of citations on this. And also we should remember that our part writing and counterpoint teachers all scolded us to write consonances on strong beats. So I represent these sets as the probability of occurrence within the corpus to approximate peaks and valleys in consonants. Things with higher probability are going to approximate higher amounts of consonants. So here, your major triads occur most frequently in this corpus. They're going to have the highest number. Dominant sevenths occur, pretty frequently. They'll have a relatively high value. And then dissonances like O27 will have very low values. And I do this with zeros and without zeros. And then I do basically the same thing with scale degree sets, which are OPC sets such that scale degree 1 equals 0. So this being a tonic triad, it has scale degree 1, 3, and 5, which in a Mod 12 universe would be 0, 4, and 7. And I take the probabilities of those two, of course. with a zeros version and a non-zeros version. And so let's see which one works the best. So last night it seemed like a good idea for me to edit my Spanish. Yeah. So the with zeros approach, you get some pretty good results with the note onsets, and then when you just do the binary version, it gets worse. And then when you use the without zeros approach, it's much worse. Pitch class change performs pretty well. Again, the binary version performs worse than the non-binary version, and worse than the other ones is the without zeros version. Set class probability is even lower in both versions, and scale degree probability is the lowest yet in both versions. So what you're seeing here is the parameters ordered left to right by most successful to least successful, where note onsets perform best and scale degree probabilities performing worse. I want to draw one thing to your attention, though, that the one sort of outlier there is the Bach corpus, which actually doesn't take a dip when you go to set class probabilities and scale degree probabilities. He continues, his corpus is pretty well metrically predicted by those parameters. And I'll talk about why in a second. So what this all shows, this first shows that zeros are really important in this approach, which wasn't part of my research question, but was a sort of interesting fallout. So this corpus-based conceptualization of meter is as much about silence and inactivity as it is about events and activity. And I'd like to test this on, do a behavioral experiment to see whether this corpus property is reflected in the way that participants respond to stimuli. It also shows that note attacks tend to be more important than harmonic parameters. So the loudness-oriented parameters were better at predicting the meter than the harmonic parameters. It also shows that of the harmonic parameters, it was pitch class change and not measures of consonance that were the most useful harmonic parameter for meter finding, at least out of those that I tested here. And this actually is reflected in behavioral studies, that people respond to pitch class change as a good way of finding strong beats. And then with the Bach example there, note attacks aren't always the most useful. That and this suggests that different repertoires might express metric accent with different parameters. So harmony is useful in Bach. And that actually makes a lot of sense, because in the chorales there's a pretty consistent magnitude of note attacks, that 4 people are always singing at the same time, right? There's always four voices. And so there's going to be a pretty consistent magnitude of note attacks, and so you're going to have to rely on some other parameter to express metric accent. And it also shows a flexible and theory-neutral approach to meter. So, returning to my initial research question, does harmony play a role in metric expression, or are the metric accents simply a result of the loudness that comes along with note attacks? Well, this shows that this is a really complicated and intertwined question. And here's an example of how those things are intertwined. An example that exhibits many of these points. This piece that we all know. Because if you ask the note attack algorithm, what's the meter? It's like, I don't know. It's a bunch of 16th notes that are occurring in a row, right? But if you give it the set classes and the pitch class, the scale degree sets, it says, okay, things happen at the 16th level. There's a half note pulse. There's a whole note pulse, and it even recognizes that there's 8 measure groupings in this piece. But it also says that there's a 3/16 note pattern that happens in this piece. Yeah. Well, and then and the thing is, it makes sense. The set classes do group into groups of 3. The same sorts of set classes occur. The same pitches tend to recur every 3 notes. And then when we move the window, when we start our window in different places, you get different kinds of 3 patterns. And this is because it's responding to the what has been called the clave rhythm in this piece. So that it's seeing these groups of 3 and being like, there's something metric about that. There's something metric about this triple grouping that occurs in this piece.
They seem like natural accents.
Sorry?
Natural accents.
Natural.
Natural.
Yeah. Fun question if you're interested. So anyway, thanks. That's all I got. Since people have been plugging their books all weekend or all week, but hopefully before the next MCM, my book Corpse Analysis of the Tonal Tradition will come out. So watch out for that. Thanks.
So any questions from the audience?
Yeah. I want to ask if do you consider like when a change of pitch in the direction of a phrase as an accent, or only when there is a peak on the volume of the note?
Yeah.
Because
right. The only things that I'm doing here are. So the question is whether the distance between the notes matters or something. Or
when you have a phrase that suddenly changes the direction.
Yeah. No, while that is absolutely something that is important for meter finding, it's not or for accent. That's not something that I tested here. Yes. Right. So like for instance,
you know what I mean?
Yeah.
Okay, right.
Because like if we're meter finding in the Bach piece, where did we go? There we are. Like the fact that here we've got this huge registral change, that's going to make that feel accented, right? Also duration. That's a thing that I didn't test, which is also important for accent. I mean, all of these things are important for accent, but I wanted to specifically look only at events that could relate to harmonic change and note events, as opposed to transitions between events. Yeah.
Thank you. So I like the thing you didn't say about your last kind of hypothetical example, and I really like. I think it's a cool idea that there might be kind of mixtures of different kinds of meters in different proportions and something like this. And I like also that your procedure. I mean, you just got kind of pushed into talking about accent, but actually, I think the procedure you're using here is more focused on finding patterns and periodic patterns than necessarily just where the accents, which I think is a big positive move forward. That's my personal opinion.
Yeah, but the thing about that though is that people are going to come back fiercely and say that's grouping and not meter, right?
Yeah.
Because it's because then you're looking for patterns and not for accents, and I think that we probably reacted too far against separating them.
Separating, I agree. Yeah, that's exactly right. The meter is kind of grouping. I mean, it is a distinct phenomenon because of this. But yeah. Okay, so I had a question too that I wanted to ask, which is obviously I think judging on from your last example, real meter finding that a human does depends on multiple of these factors, right? and you tested them independently. Did you look at what kinds of mistakes they made? Did they make similar kinds of mistakes, which could tell you if they complement one another or not? Does that make sense?
Is the they in that sentence?
So they meaning the different models.
Yeah. Oh. Whew. That's a really good question that I'm not going to have a satisfying answer to. What I can say is I was often surprised at the mistakes that it would make, and I would then look back at the piece of music and be like, gosh, I never noticed that C sharp occurs every 3 half notes, right? but the computer found it, yeah.
So it would make mistakes of period, like finding the wrong.
Yeah. The thing is, the computer's always right. It's just
right.
it's just not right in the way that
Runs to the ground. True.
Yeah.
Yeah, thank you very much. Since you are mentioning the duration as an additional feature that you could also add in your analysis, I would personally suggest to have a look to David Lewin durational interval vector, unfolding duration. It's not a very famous kind of construction in American music theory. I have the impression it was a little bit forgotten. Yeah. It's David Lewin.
You're talking about the non-commutative algebra, the non-commutative group of ribbon iterations?
Is what it's using, for example, in this famous music theory phenomenology and perception article. And I think it's a very interesting computational model of Husserl perception, which so bidimensional perception and sort of tension, potential, and it fits very well with this vector approach that you have used for harmonic and particularly with the peaks, because it's really suggesting that when you're listening to music, you are kind of moving in a paysage, in a kind of world in which you have mountains and peaks, and your perception of the meter is really a way of looking at the world. And it would be nice to.
I'll
Would be nice to see.
Thank you for your talk. It was really interesting, and I think it's great that you're going to use humans to explore this further. Because I was, you look at the first example of music, the one measure that you were studying there, where you got the quadruple meter, and because I was hearing faster pulses, and that's in the imagination. Pressure wrote a good article about the imagination and pulses. And then when we experience louder onsets, per se, we can conclude that there are more pulses on that particular onset, as you demonstrated. So the depth of pulses and the depth of meter, minimal meters. So to have a pulse, you have to have a relationship between two pulses to have an actual sense of a meter. So when you experience the duple meter, or in that piece, that Triceo that you're, the 332 that you're talking about in that piece, then becomes a unique selection of time points in the metric hierarchy. So you have two strata, one rhythmic and one metric, and so they work together, and so you can separate out. But yeah, I would argue that that's a rhythm, not meter.
Yeah, that's right. I think what is fun about the autocorrelation approach is that it doesn't have to be hierarchical. And so you could argue that means that it's not necessarily metric, that it's only metric when it happens to find two levels of pulses that align. That it will also find rhythmic patterns, and it will also find melodic patterns or something like that. And you could argue that those aren't metric, which is what you're doing, right? I like though, being able to start with an approach that doesn't make any of those assumptions, and then we can go in afterwards and say, oh, that's interesting that it still finds this, even though it doesn't have the hierarchical, doesn't assume hierarchy or something like that. Is that, yeah.
Okay, that's yours.
Much in that same spirit, there is this work by Anja Volk on the inometric analysis. Are you aware?
Oh, yeah.
So she's looking at local meters, so some local regularities where a metronome can tick for at any period, and then you look at the incidences of all these local meters, and you get the weight function, which often is a kind of phase shift of the actual metrical hierarchy. But this is not an assumption. This is really the music speaks to you and plays with it.
We have to share that citation with you.
Yeah.
All right. Thanks, everybody.
Thank you very much.